So next step is to create my setup, and I will do it from scratch by tapping here, create new setup. So here I can define the material to be used, so it's aluminum, and I can select within different material here. I can define thickness and size of the component to inspect. Next step is usually the probe selection, but since my probe is already connected to the instrument, this step is skipped, and I'm now at the scan definition, where two choices are possible: clock-based acquisition or encoder. If you select clock-based acquisition, the default acquisition rate of 250 Hz is high enough for most of the inspection you will do eventually. So what you have to maybe change or define is the typical probe speed here. So this is really the speed where you normally move the probe. So the default value is 25 millimeter per second, so about roughly 1 inch per second. But of course, that generates about 10 samples per millimeter at this acquisition rate, so you can move faster. It's always good to put a good approximation of your real speed, especially when you're on a clock-based acquisition, because if you use a probe that has 2 rows of coil, they will look more aligned on the C-scan if you're really moving the probe at the typical probe speed that you have defined. If you move the probe too fast, the 2 rows of sensor will not be aligned on the C-scan. Of course, using an encoder will realign everything. But for now, it's a clock demonstration, so you will see the impact of moving too fast or too slow compared to the typical probe speed. Next step is the scan definition, where you define the size of the scan you want to do. So right now, the size in x-axis, which is the scanning axis, is 1000 millimeters, so 1 meter long. So this is the length of scan that's going to be saved when you save data. You want to save longer data file, you put a higher value for the size here. The y-axis is the probe axis, so index axis, and you cannot change the size because it's corresponding to the probe width. So depending on the probe you have selected, the size here will change. The only control you have is on oversampling. Oversampling is a function to do channel interpolation, to increase the resolution and have a smoother image of the defect on the C-scan. You don't want to use oversampling, and you want to use only the real data, so you just press none for the oversampling. And you can see here the resolution has changed to the real probe resolution. If I put 2x of resolution of oversampling, my resolution is divided by 2 because it's interpolating one channel between each real channel. You can keep the default setting. Next step is data definition. So high flex probe is a very special probe because it can support 3 operating modes. Impedance mode, which is really a general purpose mode where the data or the channel are sensitive to any crack orientation. It's good for surface breaking defect. This is what I will use for this demonstration. The other mode possible is long single driver mode. So when you're in long single driver mode, you have 2 C-scan, axial and transverse, because the probe will have some directionality. One C-scan will be sensitive to axial crack, while the other one will be sensitive to transverse crack. The long mode is better if you want to do subsurface defect detection. It's going to have a better penetration. If you are concentrating on surface flaw, you're better to go on short double driver if you want to discriminate axial and transverse and have a better liftoff immunity than the impedance mode. So that's the 3 choice, and for now I will stick to impedance mode. I'm working on aluminum, so I will reduce the frequency slightly to a value that is more typical for that material. I can change the gain, but for now 32 dB is okay for that probe. The next step is the data processing. So you have the possibility to add low pass and high pass filter. I will not add any filter for now because when you do the initial calibration, especially based on liftoff, it's important to not have any filter, because when you create a liftoff response, very often it's going to be filtered by the high pass filter. So initially you don't want to have any filter for the first calibration. Next step is for the automated calibration. It's the calibration point you might want to use in the future for automatic calibration. So these are default. They are placed there to be used by you if you need it. So we put a notch, which could be a long defect that you use for calibration. We put axial and transverse notch if you use a probe with 2 sensitivity direction. And we put liftoff here because that's often a reference point we use for calibration. You can add more calibration point if you want to create sizing curve in the future. That's going to be the topic of another video. Next step is the calibration itself. So this is default value and it's only for automatic calibration. If you use a manual calibration based on liftoff, you don't have to care about this one. But if you really want to have a precise calibration on a known reference where you want to have a specific voltage for the defect and a specific angle, then you have to use this. And the value that is defined by default is just suggestions. It might not be one you want to use. It's all depend on the application and the signal response you have on your sample. So we're going to cover that later in the video. Next step is the sizing curve, and again there is no default sizing curve in the system, and I will not create them for now. That will be the topic of another video. Indication code, you can keep those or add your own indication code. This is for the reporting purposes. So if you know that you are looking for cracking, for pitting, for holes, for corrosion, you can define different indication code that's going to be used for reporting. And finally, it's the display options. So personally, I like to set my display like it is right now. So there's 3 sections here important. The first one is what we do on stop. So if you have zoomed your C-scan and you stop, what you want to do, go back to the default scale, full scale, zoom to the content of the data you have acquired, or keep the current scale. I like to use that, especially if my C-scan option here is set on a specific scale. So if you remember, the part size was 1 meter long, but 1 meter long on a small screen, it's tough to see the data correctly. So you can define a specific scale during acquisition, so like here 300 millimeter, and while you're scanning, when you stop, you will only see 300 millimeter at a time, and when you stop, this scale will be kept. If you want to see mini strip chart on the Lissajous, you can activate them from here. And finally, this is your layout option. So with an impedance probe, I only have one C-scan, so I will just select that C-scan layout. And I click Finish. So my setup is created, but not saved yet. It's just in memory. I have my inspection created, so I can start working. Maybe before working, I will identify here a data file name when I save my data. So I'm going to put that on, let's say, scan. So that's going to be the file name with a counter. Each time I save a data file, it's going to be named scan 1, 2, 3, 4.